Let's begin. So, you who came today are in luck because we will be covering material that will be on the exam. Some of it you've already covered, but we'll cover it today from a somewhat different perspective. And I will tell you explicitly about one of the problems that will be on the exam. So, you get to hear it first. Other people, they might forget to watch the video and then they'll be in trouble. But you lucky people will know that there is an exam problem on probabilistic CYK. So today, we're going to provide some introduction to that, but that's what we're building up to, is the solution sort of to this problem that will be on the midterm. What we'll be starting off talking about is treebanks. And treebank is basically a big corpus that has been syntactically annotated. Can also be semantically annotated, but for our purposes, we'll say it's syntactically annotated. And from that, you can learn a probabilistic context-free grammar if it's annotated, if it's phrase structure annotation. And you can use such a grammar with the CYK or CKY algorithm to parse sentences, and it will do cool things like disambiguate the sentences for you, the parses for you, because you can choose which parse is most probable in a way is most like the sentences that you find in the Treebank. So that's an overview of what we're going to talk about today. And we're going to start off by reintroducing treebanks. So what did I just say a treebank was? Or what do you know about treebanks? Who here has heard of treebanks outside of this class? Anybody? So who here has heard of treebanks in this class? Okay, a few people. What is a treebank? Yes, please. Okay, it's a corpus of syntax trees for sentences. The best known of these, in a way, is probably Penn Treebank, or PTB, which you'll use in one of your assignments, actually, in part of speech tagging assignment. But basically, they took a bunch of years from the Wall Street Journal and a bunch of other spoken language, other corpora, and they annotated the whole thing by dividing it into syntax trees. And then you can train on this data to make more syntax trees from new data. So there are two ways of encoding the grammar of a language. You can do it explicitly, so you could go and you could write out like context-free rules, for example, or you could learn context-free rules and you could represent them explicitly. The other way is implicitly. So if you have a big corpus of trees, a big collection of trees, these imply certain kinds of constituents that can exist. Certain kinds of rules are implied by the treebank. And nobody has gone and written out S goes to NPVP, but that's implicit within the annotations. So how this usually works is you have a parser, a heuristic kind of parser that goes through and generates parse trees for all of the sentences in the corpus. And then some poor beleaguered graduate student in linguistics probably goes and fixes each of those trees, fixes each of those parses, so that it fits the tests for constituency. We talked about this briefly when we were talking about syntax. There are ways of testing whether a sequence of words form a constituent and whether they should be dominated by the same node and only those words be dominated by that node. And so what these Treebank annotators do is they go through and they annotate according to those tests. So they fix all of the trees according to those tests. So this is a lot of work. Actually, both approaches are a lot of work. Like writing out rules by hand, lots of work. Making a tree bank, also lots of work. But it's different kinds of work. And we'll learn in this lecture about the second option, about creating tree banks and then training grammars like PCFGs or probabilistic context-free grammars on those tree banks. So the first big tree bank, as I mentioned, is the Penn Treebank. And it's still widely used. It has a number of different corpora together. One of them is the Brown corpus, which is the first major electronic corpus of English. There's the Air Travel Information Service corpus, Switchboard corpus, and the biggest part is drawn from the Wall Street Journal. It was produced at the University of Pennsylvania, which is why it's called the Penn Treebank. It's only about 1 million words, which might not seem very big, but for a tree bank, it is pretty big. It has 17,500 distinct rule types. So that's a lot of different types of rules, a lot of different types of constituents. And a lot of the rules are kind of flat. They like have lots of things on the right-hand side of the rule. And a lot of them only occur in one tree, which is problematic, but that's the way it is. There are other tree banks. There are both phrase-structured tree banks and dependency tree banks. The other tree banks are typically smaller than the Penn Treebank. It takes a lot of work to make a tree bank. And dependency tree banks are very popular right now because you can do a lot of nice linguistic tasks with dependency grammar. But there are also plenty of other constituency or phrase-structured tree banks in addition to the Penn Treebank. The best-known set of dependency tree banks right now are Google Universal Dependencies. So this is a set of conventions for doing dependency annotation, and then a group of tree banks that are annotated according to these conventions. And they exist in lots of languages big and small. And they're not immediately applicable to what we're going to talk about next because they're dependency tree banks, and it's really hard to get constituency information out of a dependency tree bank. But they're very relevant if you're thinking about training dependency parsers. We're just going to talk about context-free things, though, phrase-structured grammars. So to refresh your memory, this is what a context-free grammar looks like. You have a vocabulary of terminal symbols, the words, a set of non-terminal symbols, the phrases and parts of speech, you could think of that as, and special start symbol S, start or sentence, production rules that look like X goes to alpha, where X is a non-terminal, and alpha is some string of either non-terminals or terminals, or in Chomsky normal form, it's either 2 non-terminals or 1 terminal, or actually null. So tree banks can be encoded in terms of context-free grammar. So if you look at this tree bank here, or this item from a tree bank, it's not a whole tree bank. This is the first sentence from the Penn Treebank. So all computational linguists and NLP people know who Pierre Vinton is. And I propose that we actually have a holiday on Pierre Vinton's birthday just to celebrate. It could be like Tree Bank Day. So you've got S up here, and then you've got the things that S is rewritten as. NP subj, DP, and a period. An NP subj is an NP, a comma, an HP, and a comma, and so on down the line. So you can see pretty easily how this translates into context-free rules, right? You can just read the context-free rules off of the tree. Particularly if you like programming in Lisp and you love parentheses. Which I do. So tree banks are great. But tree banks also have problems. And you should be aware both of why you should appreciate tree banks and what some of the limitations are if you're ever going to use them. Which, if you do much NLP, you probably are. Even if you don't use them directly, use them indirectly because the tools that you use were trained with tree banks. This is why you should have great respect for tree banks and also why you should be cautious around them. How do you make a tree bank? Well, there are a lot of things you have to do. You have to develop an initial coding manual that says how you decide everything when you're making the decisions. You have to have linguists to define the categories and the tests. You try to foresee as many complications as possible so that these will already be consistent from the beginning in the tree bank. You have to develop annotation tools, which is boring, but you have to do it. And you also have to collect the data and get copyright on the data and all sorts of permissions and all sorts of issues like that. And you have to pre-process it so it's in a consistent format that can be used by the annotation tools and so on. Then you have to automatically parse the corpus. So you have to have some parser that will already work on the corpus. And you have to train a bunch of annotators, coders, who will learn everything that's in that annotation manual, which is probably several hundred pages long, and apply that in correcting trees. Now, these coders are generally they generally don't have PhDs in linguistics or anything. So they often don't understand the decisions that they're making. They can apply things reasonably well, but it takes a lot of training and a lot of experience for them to actually know how to make these kinds of decisions and get the trees right. All the time you'll come across things like edge cases that were not considered when you were originally coming up with the coding manual. So you have to add them to the coding manual and continually revise this. And then when you find something and you make some change in the coding manual, you have to go all the way back through the tree bank and fix all of the instances of this to make everything consistent. So this is a lot of work. This is expensive and time-consuming. So you should respect tree banks. They require a lot of skill. They take many years to make, and they are expensive. So this is why there are not a lot of tree banks as big as the Penn Treebank. It takes a lot of money, and it's hard to convince like funding agencies let's go make a tree bank. Other tree banks are not good enough or not big enough. Let's spend millions and millions of dollars making a new one. You know, it's really hard to convince them of that. But you should be cautious around tree banks. You shouldn't believe something just because it's in a tree bank. So because they're so expensive, it's really hard to replace them. So they have a long lifespan, not because they're perfect, but because you can't afford to make new tree banks of the same kind. You can maybe get money to make a different kind of tree bank, but you can't get money to fix a tree bank or expand a tree bank, typically. And they're produced under a lot of pressure of time and funding, and although most of the decisions are made by experts, the high-level decisions, they're all implemented by non-experts. So the implementation sometimes doesn't match the high-level expectation. So you should invest some time in understanding this. To create a good model, you need to know what you're modeling. And if you have a model and it's not performing as well as you expected, what could be the cause? What are the possible causes of your model not working the way that you hoped? So it could be that there are two kinds of ways the model could be wrong, right? You could have a bug, or the architecture of the model could be not well suited to the problem space. So that's the one that most people with a computer science background doing NLP focus on. If things are not good, then my architecture is bad. I need a better architecture. But sometimes there's a simpler explanation why things are not working right. And that is that the data that you're using has problems in, and you don't understand the data. You don't understand what went into the creation of the data, and so you're not using the data optimally or making the right assumptions about what is there. So a while back, we saw this. And we noticed that we can derive production rules from a tree in this way. And you can do this with a whole tree bank. You can derive all of the rules. You know, this is trivial, right? Any of you could do this. You could, given trees formatted in this way, you could extract all of the production rules. And you could count them. You could count how many rules there are for S, how many rules there are for NP sub 1, and so on. So here are some examples of some rules from Penn Treebank. This is the most common rule. It occurs over 40,000 times, and it means that it's for a kind of prepositional phrase. So IN is a sort of preposition, and NP is a noun phrase. So that occurs a lot. And so does S goes to NP sub VP. Then there's a very few rules that occur a lot. And then there are many rules that occur some, and there are even more rules that occur very rarely. So all of these rules only occur 10 times. There are a lot of rules In fact, the largest number of rules only occur once. So this is a little bit of a problem. This is a problem in Penn Treebank, that the tree structure is too flat and not general enough. And so that you end up with this sparsity problem. You have all of these cases that are unlike any other case. So it's divided into a training and a test set. And if you actually, or a training and a dev and a test set. So if you look at the intersection between the training section and the dev section, then that covers 78% of the rules in the dev section. That means that there are 22% of the rules in the dev set that never occur in the test set, which is kind of bad, right? But that's what we're working with. So it's really hard if you're applying naive methods, and if you don't know that, it's really hard to get above that 78% on the dev section, if you're running on the dev section, because a lot of the rules just aren't there. So this shows what the distribution of rules looks like. So you have a very few rules with very high frequency, and it drops off precipitously. And then you have a long tail. And if you look at this in log space, then you see it's like this. So how do we know we're parsing well? So let's say that we can take a tree bank and we can train a parser that can make more trees like the trees in the tree bank. How do we know if we're doing a good job? How would you evaluate this test? Okay, see how close the parse trees match. So how would you do that? The what? I can't hear you. I'm checking the probability. Yes, that would be one way. But what do you mean by checking the probability? The probability of what?
Of all the trees and just finding the best probable trees and just figuring out whether these make sense or not.
So that can help you pick the best tree from a parse. But let's say our goal, is given a parse tree for given a gold parse tree from Penn Treebank from the test section, and a parse from the parser. The gold parse doesn't have any probabilities to it. It's just what it is. So given those two trees, how do we tell whether we did a good job? Yes? Yeah. So you can do check precision. So in this case, precision would be what? How many? Or you could say how many constituents in the parse or in the gold tree. So if you can do precision, you can also probably do recall. So what would recall be? something like that. We'll get to this. So Parseval is an evaluation for parsing, and it's based on precision and recall. So if you have these are the constituents in the gold standard trees, and these are the constituents in the output parser trees, then our goal is to maximize the intersection between these two and minimize the size of these non-intersecting parts, the errors. So these would be false negatives, and these would be false positives. We can do labeled recall and labeled precision, and then cross bracket. The labeled recall is basically just the number of correct constituents in the candidate parse tree S over the number of correct constituents in the Treebank parse of S. And likewise, labeled precision is the number of correct constituents in the candidate parse of S over the total constituents in the candidate parse of S. So you can take labeled precision and labeled recall as two metrics. There's also cross brackets, the number of cross brackets, the number of constituents for which the Treebank has the bracketing like A, B, C, A, and B together, and then C. But the candidate parse has A, then B and C together. So you have a constituent that's right at the top, but you're switching the position of the bracketing down below. And that's cross bracketing. We'll talk mostly about recall and precision. So this brings us to the F measure. There will be an exam question, at least one, on the F measure, on F1 or F something. So you should know this formula. What is F1? Stated informally, not in terms of the formula. This should roll off your tongue. F1 is the harmonic mean of precision and recall. Repeat that to yourself. F1 is the harmonic mean of precision and recall. You need to know that. Okay. Well, there's a generalization of F1 is the F measure. And here we have beta, this parameter beta. And if we increase beta, then we increase the numerator. Basically, if we increase beta, then we increase the weight on what? On precision. So F2 weights precision more than recall. F1 half, or F.5, weights recall. So this brings us to the reason that I've gathered you here today, which is to talk about probabilistic context-free grammars and specifically be thinking about how you could apply these to CYK or CKY parsing, because there will be a problem, as I mentioned before, on the exam about this. It will not be a hard problem if you know what is in this lecture, but it will be a problem, and so pay attention. So we've got two related problems. One is recognition, and one is parsing. So if we have an input sentence W and a context-free grammar G, then recognition is asking if W is in the language G, and parsing is is asking if there are one or more derivations for W under G. So when we first learned about CYK or CKY in this class, then you learned the algorithm for recognition, right? But to do parsing, you don't have to change the algorithm very much. What did you have to add to the CYK algorithm in order to get a parse tree rather than just return true or false, depending on whether the grammar recognized it or not? You just need a back pointer to the tree itself. And then when you get up to the corner and it's F, and you just pull that F up and everything follows the back pointers, and you pull the tree out of the parse chart, and all is well. So parsing and recognition are related to each other. We have a good way of doing both of these with a grammar we've learned from a tree bank, and that is with probabilistic context-free grammars, or PCFGs. So these look just like a context-free grammar. We've got a vocabulary of terminal symbols, a set of non-terminals, a special start symbol, and you have production rules of X goes to alpha. And this is all the same as context-free grammars, except for each production rule, then there is a positive weight. And these are constrained such that for every non-terminal on the left-hand side of the rule, all of the rules that have that, their probabilities, their weights must add up to 1. So the probability of every rule that has S goes to something, all of those add up to 1. So it's a probability, right? Sums to 1. So that's all there is to a PCFG. Very simple. And very appealing. So here's a sample PCFG. Here we have the rules, the weights. This is constructed, it's not based on data from a tree bank, it's just what Jurasky and Martin made up by hand. But it gives you the idea. So for S, you have 0.8, 0.15, and 0.05, adding up to 1. Here is the important part. The probability of a parse tree under a probabilistic context-free grammar is the joint probability, or the joint probability of the parse tree and the sentence is equal to the product of the probabilities of all the rules R used to expand nodes N in the parse tree. So this is really simple. What does this mean in informal terms? If you translate it out of the little formula here, simple little formula, you can express it pretty easily in words. What does it mean? Yes? Yeah. You're just multiplying each expansion. The probability for each expansion, you're multiplying them all together. So it doesn't really matter what direction you do these, how you traverse the tree, just so long as you have all of the probabilities for all of the expansions. You multiply them together and done. So this is nice, because let's say you have a grammar, a PCFG, and you have the sentence, I saw the woman with a telescope. Now this is ambiguous. Your grammar is probably going to generate two different parses. one where you use the telescope to see the woman, where you have the prepositional phrase attaching one place, and one where the woman has the telescope and you have the prepositional phrase attaching another place. So let's, with a context-free grammar, you don't know which one to pick. Context-free grammar says, they're both good. I recognize both of them. I'll give you both parse trees. You put into CYK, you go and pull the S's out with your fingers, and the back pointers pull up both trees. Well, it's not always desirable. Sometimes you want the most natural parse, the one that is most like what is in the Treebank. And if you have a PCFG, you can do that. You just calculate the probability for these two different parses, and whichever is highest, you take that one. So it provides a way of disambiguating parses. So here's an example of the same thing. So we have these two sentences. Can you book TWA flights? Meaning, can you book flights for TWA? And can you book TWA flights, meaning, can you book flights on TWA? TWA used to be an airline. And for some reason, the authors of your textbook are obsessed with TWA and with air travel in general, but particularly with TWA, Trans World Airlines. So that's the example we're stuck with. So that you have these two different parses that are possible for this sentence under a particular grammar. And if you have such a grammar and you have these productions with these probabilities, then you can take the product of all of these numbers and the product of all of these numbers for this parse versus this parse, multiply everything together, and you get, for book flights on behalf of TWA, you get 1.5 times 10 to the negative 6. For book flights that are on TWA, you get 1.7 times 10 to the negative 6. So we prefer which parse? This parse. We prefer the tree on the right because it has a higher probability. So on the exam, you'll be presented with a grammar and a sentence. And you will be asked to apply CYK to the sentence with PCFG, so with probabilities. So you'll build up your parse tree, and at the same time you can build up the probabilities. And when you get to the top, you have the probability of the whole parse. I mean, you can do it a variety of ways, but you have to show this in your parse chart. You need to show your probabilities and the operation of the CYK algorithm building the parse trees. So any questions about how you would do this? This is really pretty simple, but it asks you to combine CYK and PCFGs, which is two great tastes that taste great together. Can everybody do this? You feel good about this? I expect you all to get perfect scores on this exam question because I told you. I mean, we're going to make it a little bit tricky. You're not going to be able to rely on your knowledge of English to do this. So you have to actually know how the algorithm works, and you have to actually know how PCFGs work. But if you know that, you can do it. Yes. I would suspect you'll end up with multiple possible parses. Yeah. Yeah, you have to use a parse tree that has a higher probability. And there's no way to cheat on it. So there are no shortcuts. You just have to actually do it. But yeah, there will be multiple parses. You have to say which one is correct and what its probability is. Which one is highest probability and what its probability is. Any questions? Any more questions? We can't really observe in retrospect how you did it, but there are two different ways of doing it. Sometimes, so if you're implementing this, actually, you would probably do it simultaneously. So you're computing the probabilities as you move up the parse tree. Are we expecting them to do that? Are we allowing them to just find the product of the probabilities at the end? Yeah, you do have to draw the tree. Yeah. There isn't, or there is? Right. Right. Yeah. Bring a calculator, by the way. A pocket calculator, something that doesn't connect to the internet, or that doesn't have like infinite memory. But you would do well to bring a calculator, because as you're calculating the probabilities for the trees, you can just write everything out, but it's going to be awkward and there's not going to be a lot of space. So word to the wise. Cheat sheet, calculator. So what can you do with a PCFG? Well, like CFGs, they can be used for both parsing and generation, but they have advantages going both directions. So the advantages, so CFGs are good for precision parsers, like when you want to exclude things that aren't part of the grammar. You want to say this is explicitly bad and this is okay. But PCFGs are good for robust parsers because you can do different kinds of smoothing with them. So they will accept pretty much any sentence with the right vocabulary. Just some of them will have very low probabilities. So they don't fail and tell you, they don't have to fail and tell you, oh, this sentence is ungrammatical. They'll give you some parse of each of the sentences, no matter how improbable. So that's nice. They also have built-in capacity for disambiguation, which is what we'll be talking about on the exam. You can know which parse is most probable, most like the sentences in the Treebank, if you use a PCFG that's trained on that Treebank. PCFGs can also be used for generation. So they will generate sentences that, CFGs generate a lot of crazy sentences because there are a lot of sentences that are kind of grammatical, but they're not very much like real sentences. With PCFGs, then it's more the case that you have a lot of, the sentences tend to be more syntactically like sentences in the Treebank that the PCFG is trained on. So that's good. So where do you get the probabilities? Well, you get them either from a Treebank or from a corpus. And if you get them from a Treebank, it's really easy. It's just the number of times the rule alpha to beta occurs over the number of times that alpha occurs. It's that simple. Well, what if you want to get them from someplace other than a Treebank? Well, you can do it, although it's more complicated. So you can parse the corpus with your context, with a context-free grammar, and then count the rules for each parse, and then normalize. But there's a problem, which is that most sentences in a corpus are going to be ambiguous. So you have to keep a separate count for each parse of a sentence and weight each partial count by the probability of the parse it appears in. So you do this kind of inside-out thing. People don't do this as much. People tend to do this. So here is a toy example of generation with a PCFG. Actually, this is boring. I'm going to skip it. So one way of looking at PCFGs, not entirely sound, but a way of associating it with a common trope that we've discussed in this class, is to view them as being like a noisy channel model, kind of. So you start off with PCFG. The channel model here gives you a derivation, a parse tree, basically, a derivation. And then the noisy channel removes everything but the words, with the terminals. And the parsing problem is the decoding problem here, given the words, trying to figure out what the derivation was. So all is not well in PCFG land. In CFGs and PCFGs, then each rule is independent of each other rule. They're context-free. And this can be a problem. So if we have the rules F goes to NP VP and VP goes to VNP, and we look at an actual Treebank, then the first NP, the subject, is a lot more likely to be rewritten as a pronoun than the second NP, an object. But we don't have a lot of choice in a vanilla context-free grammar, but to treat both of these as NP. Actually, Penn Treebank did try to get around this by calling this NP NP sub. But you can't do that everywhere that this sort of thing happens. And there's no good general solution to this problem in a vanilla PCFG. The fact that these NPs have different statuses. Another problem is that PCFGs are not sensitive to words. So if you go higher up a tree, then a PCFG has no way of knowing what words will appear below. You can only see down one level. But it turns out that lexical information is important. That is, information about what words are there. It's important in selecting the correct parse, as in the example thing here. So the verb sent subcategorizes for a destination. It prefers the destination reading. It favors VP attachment. But there's no way of expressing that with a vanilla PCFG. So how could we solve this problem? What could we add to a PCFG, or how could we change a PCFG to address these issues? Yes. Okay, we could tag nodes with features. What kinds of features would we want? Right. So you could have information in the nodes, like in the. So one way of doing this is rather than having just S or NP or VP, you actually have structure of features that tell you where syntactically a word is and allow communication up and down the tree and across the tree in various ways. So this is actually one approach. Approaches that adopt, like approaches to syntax that adopt this point of view or this technique are sometimes called lexical, because the idea is that you have information about words built in to the syntax. Although there are non-lexicalist approaches to the same problem. But what we're going to talk about is a theoretically not very sophisticated, but nevertheless useful approach to this problem, and that is probabilistic lexicalized context-free grammars. So there's an important concept in syntax, which is the head. For our purposes, the most important word in a phrase, in a constituent, is the head. So the noun is the head of the noun phrase. A verb is the head of a verb phrase, and by extension of the whole sentence. A preposition is the head of a prepositional phrase. It's the word that determines the type of the constituent. So what we do in probabilistic lexicalized context-free grammars is we augment the label with the head. So we do something like this. So rather than having just NP here, we have NP workers, because workers is the head of the noun phrase. And instead of just having S, we have S dump, because dump here is the head of the sentence. The head of the verb phrase and the head of the sentence by extension. And so on for every other node in the parse tree. Well, what does that buy us? Yeah? So verbs are the heads of sentences. So basically a verb is like a function that takes nouns as its argument. So it's the head, and they're the dependent. So that's why a verb dump percolates up here to the top. So what does this bias? Let's say we lexicalize our whole tree bank. The bad part is we've now got a whole bunch more rules. If we just replace each S, some S's are S dumped, some are S grand, some are S, we've increased the sparsity of our tree bank and increased the number of rules by a large magnitude. What have we gained? Yes. Right. So when we see the same verb, so cases where, like the sent case that we looked at just before, where the verb sent picked out a particular kind of structure. If we had a lexicalized tree, we could learn that directly. That would be directly encoded in the tree bank and therefore in our PCFG. So these kinds of dependencies would be captured. What about the what about these structural dependencies? Well, that's still a problem, but it's less of a problem because if we're worried about pronouns, for example, if pronouns are the head, those are going to be a lot more likely to occur in the rule in rules like S goes to NP VP, where it's NP pronoun VP, and other nouns are going to be more likely to go in the rules after a verb. You can learn all of that. So there are a lot of fancy ways of looking at rules in a lexicalized grammar, including treating them as feature structures, as we were talking about just before. But we're going to look at them in a simple way. So a lexicalized grammar is like a vanilla PCFG, except with a lot more rules. So our rules, instead of looking like S goes to NP VP, they look like S dump goes to NP workers VP dump. So these grammars are huge, sometimes impractically huge. But they can be used with the same algorithms that we've already learned. So you can use them unmodified with CYK. They require more training data than vanilla PCFGs, but they do better with probabilistic patterns than PCFGs did. And actually, in most contemporary applications that use PCFGs, they're lexicalized PCFGs. Questions? Yes? Yeah. Oh, what we gain? So we talked about two kinds of dependencies. Structural dependencies and lexical dependencies. And lexicalized PCFGs help with both of these problems. So for structural dependencies, they help because this kind of NP is going to have different words, different heads, than this kind of NP. So it differentiates these two classes of rules. So that's one kind of thing that lexicalized PCFGs help with, is structural dependency. The other thing is with lexical dependencies. So you have situations where some verbs say, I want this kind of an argument. That's called subcategorization. And sent here subcategorizes for a destination. You send things to a destination. And so it favors a particular parse. This one rather than this one. So a lexicalized PCFG has a way of capturing this because nouns, the noun that is the head of a verb phrase containing sent is more likely to be something related to a destination than anything else. So statistically, this ends up helping us to capture those kinds of relationships. So basically the idea is that it helps with structural dependencies and it helps with lexical dependencies. Other questions? Any questions about the exam? Yes. You have to generate parses. You will. You'll have to apply CYK. You have to apply parse to apply CYK in a way that generates multiple parses in a parse chart, and then you'll have to be able to say which of the parses is highest probability. Other questions? Yes. And you need to know about the Viterbi algorithm. You ask people on it. I can't tell you that. Maybe in very small font. It's precious real estate. Anyway, I suggest memorizing the Viterbi algorithm. I wouldn't worry too much about that, but you should know how the Viterbi algorithm works. You should be able to kind of step through it, but you don't need to be able to run it explicitly. Okay. But you might want to put it on your cheat sheet just in case, because we haven't finished the exam, so you might have given us some idea. Any other questions about the exam? Yeah. Yeah. Yeah, you are expected to know things that were not covered in the lecture that are in the book. That's why we have the book. So you'll read it. Anything else? There's going to be a lot about classifiers, and you should know about the strengths and weaknesses of different classifiers. You should know, about naive phase. You should know about logistic regression. You should know about perceptron, threefold, romance. You should know about all of those things and what they're good at, or what their advantages and disadvantages are, and be able to recapitulate that. In terms of knowing exactly how something is implemented, we don't expect you to know like how an SVM works inside. Although if you do, that's great. But you should know naive phase. You should be able to describe on paper how naive phase classification works. But there'll be plenty of stuff on classification. That's an important topic. Yes.
Saying that all the
Each. So yeah. So one each. One point each. What did we say on the? So I'm trying to remember off the top of my head. I think it's 25. I think we said 25 at some point, and I think that's what I'm targeting when I pare down the number of multiple choice questions in the exam. So yeah, so you can think of 25 multiple choice questions, 2 short answer questions, and 2 long answer questions. And the weight of the points is going to be on the essay questions rather than on the multiple choice. But the multiple choice will provide diversity. So they'll tend to cover things that are not covered in the short and long questions. So how we've done this, how did we do this last year? So my preferred way of doing it would be precision and recall. It would be to give F1. But it's annoying to calculate sometimes. Yeah, that's I think how we did it last time.
So you're more conceptualized to one right one and not get the second.
Right. So you get a point off. I guess that's what we did. Is you get a point off for every false positive, and you get a point off for you get a point for every true positive. Or a partial point for every true positive. You get the, yeah. It sums to 0, yeah. And so you divide 1 by the number of true positives, and you get that proportion of the, it would be easier just to do precision and recall. Anyway, but you get points off. You shouldn't go choosing everything, because you get points off for choosing things that are not correct, but you get partial credit. So you should be conservative, basically, and not mark things that you're not sure about. Other questions? Are you feeling confident about this exam? What? I want you to know that we shortened it considerably from last semester, and last semester was shorter than the semester before, because we don't want it to be, it's still enough to keep you busy for the whole time, but we don't want it to be like a race that favors people who write fast and think really fast. You know, we want it to be more equal. And so we reduced the length somewhat. So, but it's still enough to fill up an hour and a half. So come prepared. Do bring a cheat sheet. You know, spend some time preparing your cheat sheet, because the more time you spend preparing the cheat sheet, the less time you'll actually have to spend looking at it. That's like the best way to study, you know, is try to think, what is important, what should I put on my cheat sheet? You know, that will, in my experience tells me that will really help. And look at the list of topics, make sure you know each of those topics. If you're unsure about something, consider rereading the chapter from the book, or the passages from the book. It is a good book, actually. It's kind of wordy for like computer science majors. There's like a lot of text on the page, and they go talking about a lot of definitions of a lot of terms, you know, but they're terms that you ultimately need to know. And so do look back at the book and look at your notes for the book, and that will like provide an additional perspective in addition to what was in the lectures. So any more questions? So we're rooting for you. We want you to do well. We're trying to design an exam that will allow you to show what you know. And we have the utmost confidence in you. So go and study, and like flood Piazza with questions, and be ready on Thursday.